You are Barry.
Thank you, Doug. And I'd like to thank the organizing committee for organizing this in general. I've attended this conference a number of times and always enjoyed it, and I'm thankful to be able to present here. So I would like to present something that I worked on with one of my Eigenvector colleagues for a while here, a calibration model maintenance roadmap. Well, the general outline here is we'll do a little introduction to model maintenance and start with identifying the need for action. I'll talk a little bit about model updating methods and then instrument standardization methods and avoiding model maintenance altogether right at the end. So multivariate calibration, classification, and fault detection are ubiquitous in process analytical technology, QBD, of course, all over chemical plants, et cetera, et cetera. These models are all over the place. Model maintenance is the ongoing servicing of these multivariate models to preserve their predictive abilities. And of course, then the goal of model maintenance is to sustain or possibly even improve over time the models, given that the conditions are changing, and do it all with the least amount of effort and cost. So why do we do model maintenance? Well, there's a lot of things that can happen that make models stop working. Samples can move to a range outside the original calibration, and that is your analyte of interest or your interference go beyond their calibration range or possibly occur in some unusual combination. It's possible that you could get a new variation that's introduced into the samples. That is, you have a new interferent that wasn't there before, or you've had a variation in some physical parameter such as temperature or particle size change, for instance. A change in the sample matrix causes the relationship between analyte and measurement to change. This is an instance where changes in the sample matrix, maybe due to pH, really change the relationship between the analyte spectra and its concentration. This one always seemed a little wishy-washy to me, but I've been dealing with optical emission spectroscopy lately, and it seems to happen there across different instruments. A change in the hardware causes the analyte measurement relationship to change. So when you do instrument maintenance, change the fiber optic, change the source, any number of things like that. So before a model goes online, develop a plan for maintenance. And this just seems sort of obvious, but in fact it's amazingly not routinely done, as near as we can tell. It is in some places, but in a lot of other places, and we've seen it in chemical plants, it was assumed that the calibration model would last forever. And instead, you need to assume that an updated or new calibration model will eventually be required, and have a plan for how to detect the problem and what you're going to do about it, because it will happen, and put it in the budget. And it's amazing how many times it's happened in chemical plants that a method has gone online and made money because of its existence, and yet after 2 years, when it stopped working very well, a method that originally cost a €250,000 to implement, they couldn't find 10,000 euros to fix, to get somebody to spend some time with the data and update the model, and it just went back offline again. So put it in the budget. You know, often that's one of those things about it comes out of somebody else's pot of money, and anyhow, but it needs to be thought about beforehand. And the other thing is to measure standard samples up front. If you're going to attempt to do instrument standardization, you have to decide in the future, you have to decide on what your standard samples are now and measure them when you're developing your calibration models. So plan for registration and amplitude shifts in the data, and characterize the instrument in ranges important to the model. So how do you detect data mismatch, data model mismatch, and performance degradation? Well, we have our model prediction statistics. So we use a lot spectral residual Q or similar measure, depends on whose package you get it out of, what they call it. Sample distance measures, t-squared or other Mahalanobis distance or similar. We use those a lot. But it's also important to have the prediction accuracy monitored via primary reference method periodically. Okay? And it's unlikely that you can get a change in an instrument that wouldn't be detected by the diagnostics, but it's possible. And especially in pharma, it's popular to do a risk-based approach where they really look at the different scenarios that might happen, think of the probability of those, and do the flow down and determine what the impact of those would be. In general, though, detecting that something has gone wrong is considerably easier than determining what it was that has gone wrong, unless, of course, you're monitoring via a reference method occasionally, and why aren't you? So we still think that's important. Just because you implement a new spectrometer online doesn't mean that you can totally shut down the wet chemical laboratory that you used to have. Diagnostic limits. Well, by default, limits for Q and T squared are typically set statistically based on some sort of confidence interval. Like we put a limit on those things and say, well, we're going to draw the line where we know that 99% of the data should stay within that. So those values are statistically based, but they're not necessarily meaningful in an engineering sense. Meaningful limits require knowledge of the process or measurement. In other words, for Q being at the 99% limit, on about that line, what does that mean in terms of how bad your predictions typically get for that and how those poor predictions affect things downstream? So sometimes it's really useful to try out scenarios and see what sort of Q and T squared values they produce so that you can relate it to actual process performance. And that can allow you then to pick some numbers of limits on these that are actually important to your process. And it might turn out that they're considerably higher than, say, where the 99% limit is. You may find that you have to go to 99.9 or 99 and 2 nines in order to get bad behavior typically in your process. And that's great because you don't want to create a lot of false positives here, so to speak. You really want to minimize your number of false alarms. So observations are needed that represent bad states of the process, out-of-spec products, failing sensors or analyzers. Some of those are pretty challenging to obtain. Some of them can be gotten, of course, also through the combination of actual data and simulation. But I'll just do a couple of examples here of detecting model data mismatch. This is a semi-synthetic example where I just took some near IR measurements of isooctane in the presence of various interferents, and originally built models in the presence of heptane, toluene, and decane, and then added xylene later, and just developed a model for this. So in normal operation, things would look like this. So here is a Q versus T squared plot. The calibration data are the gray circles. The test data are the red diamonds. So under normal operations, you could produce this T squared plot with your new data being plotted on top of your old, and things would look like this where, yeah, most of the data was still down in the lower left corner here, and then the scores plot was within the bounds of the old data. And if, of course, you were measuring with your reference method also, you could make these plots, and that is the actual measured versus predicted here for your calibration and test, and the deviations with sample number from the prediction. So this is prediction error that we're plotting there. So that's when things are running well, they look like that. If you get out of range samples, so concentrations that are typically too high or too low, beyond the range of your calibration model, then usually your plots are going to look something like this. You'll get high t-squared values, perhaps modestly higher q values, but you usually will see that on one or more of your scores plots where your samples are out of bounds. Often though, since if you're doing linear spectroscopy, your predictions will stay reasonably good in these cases, and of course you would know that only if you're measuring reference values, and so your errors would still be largely centered around 0. On the other hand, if you get a new interferent in your system, it tends to look like this, and that is often higher t-squared values, but especially higher q residual values of the new data. Scores plots, for some of them, might look fairly normal. Usually you'd see that maybe down in lower scores. But you would see, if you're measuring by the reference value, a definite shift in the data of the test versus the original calibration. And in this case, I had this interferent grow in with time, so you'd see a tracking away from 0 there in the error. And an instrument registration shift will also look something like this. High t-squareds typically, high q's. Scores on the first major components, usually not too bad. It usually results in a fairly constant offset in the system and bad prediction errors. And I didn't include this slide in this one, but I thought at one time that by examination of the residuals, it would be typically pretty easy to tell the difference between a new interferent and just a registration shift. And you know what? It's not. It's not that easy. It's hard to tell the difference sometimes. So determining the cause of the problem, it might not be obvious from just these model diagnostics. The measurement by reference method is extremely helpful. Standard samples can pin down the cause unambiguously. But then what? You need to either expand the calibration set, do a slope and bias correction, or do some type of instrument standardization. Well, adding samples to a calibration set is pretty typical. When you get out of range or new interference, that can be solved by adding those samples. The problem is often getting a properly weighted new calibration set, because then those samples tend to be underrepresented. So a solution is to upweight those new samples, usually when you incorporate those in. If your calibration set's very large, you're definitely going to need to do this if you can't measure a whole bunch of new samples. Slope and bias corrections are actually valid in some times. They're simple to do. They may be appropriate if you've gotten a constant shift in your data set, such as a new interferent, but that is at a fixed value. It's not to be used over and over, and we've seen this one too, where every day they're putting in a new slope and bias correction. It's like, no, don't do that. That indicates that there's a problem, is some variable interferent or something else is going on if you're doing that. And there are, of course, automatic ways of doing this. And of course, there's a lot of standardization methods out there. All of these attempt to estimate the response of a standard instrument from a different or changed instrument. And my favorites are direct standardization, piecewise direct. I've had some good luck lately with subspace standardization transform, and also used generalized least squares preprocessing and orthogonal signal correction as calibration transfer techniques with some success. They have different requirements, though, as we'll see here in a minute, because these three here, because they map the response of one instrument directly into another, they don't require rebuilding the calibration model. Whereas these methods actually change the data for both the calibration and your new data in such a way to make it ignore the changes in the data. And these require some model rebuilding. Maybe not any new samples, but model rebuilding. So putting it all together, I've covered the pieces here, but that is detecting the change, identifying the problem, a method for updating or correcting, and standardization methods. So how does it all fit together? Well, I actually created this on the airplane a couple of years ago. I think it was the best trip over the Atlantic I've ever had. And you start with a preliminary study in calibrations and develop that maintenance plan. And at that point, you put the model and the instrument online. And then, is it behaving okay? You know, yes, then keep using it. No, well, what's the source of the problem? So you have to do some tests there. Well, the first source could be, is it just out of range samples? And if that's the case, you measure additional samples, and then you develop that new model, and you put it back online and start again. Otherwise, if your source of the problem is a new interferent, first you have to ask, is it constant or variable? If it's variable, you really do need to add it to a calibration set and create a new model. If it's constant, you might get away with the slope and bias correction to just add that term into your modeling. What if it's really a relationship change in the instrument, like a change in the instruments or a change in the matrix? Well, is it the instrument or is it the samples? Well, if it's the samples, then you have to ask yourself, is it compatible with the old data or not? Is it so fundamentally different that I really can't combine this data with the old data? If it is compatible, you can just add new data, measure those samples, go that way. Of course, if it's not, you might get stuck measuring a whole new calibration set. And if you have to do that, then you're here, whole new set, new calibration models. On the other hand, if it's the instruments, you can decide to recalibrate or standardize. And recalibration is this direction, measure a new calibration set and on. Or standardize, well, which method are you going to use? If you're using generalized least squares or orthogonal signal correction, then you'd be in this branch, where you'd have to develop your standardization transform on the original data and create that new calibration model up here and back. And then finally here, if you're doing direct standardization, piecewise direct, subspace transform, you could just develop that standardization transform and bring that all the way back around here and not have to get a new model. Of course, it would be nice to avoid model maintenance altogether. Some models are more robust to new analytes and changes in the data than others. And it's highly dependent on pre-processing options and the number of factors in the models. We've developed a series of robustness tests in PLS Toolbox that test the model against various changes in the data, such as changes to wavelength axis shift. And it results in plots like this. Like here, if we look at registration shift in channels versus prediction error for different types of pre-processing, you can see things like this generalized least square model with pre-processing was fairly robust to registration channel shifts, whereas a model with a second derivative gets large errors real quickly if you start messing around with the registration. Well, so in conclusion, plan and budget for model maintenance. There's many elements to it: performance monitoring, problem detection and identification, standardization protocols, and remodeling and revalidating. I think this roadmap is a good starting point for a lot of applications. Not every branch of it is going to be needed everywhere, but I think it covers quite a little bit of the territory. And model robustness testing up front also can help you minimize the need for model updating. And with that, I'd like to thank you.
Thank you, Barry. So, any questions? Jean-Michel, pas de questions?
So nice talk. I think we already have discussed about that. But in the generalist square and the OSC, there is a mean for doing that. And maybe you do not talk about orthogonalization methods in depth, but there is a lot of publication about top, DOP, a lot of things for making explicit orthogonalization methods. And how do you include that in your scheme?
I think you could probably include them on the same track there. I mean, those are the only ones that I've really spent much time with, where essentially what you get, is a new calibration data set that doesn't see the changes that happened in the instrument.
Yes,
and certainly those are tools that you could do this.
Yes.
The same thing.
Yes. So what you have talked last year, how to put out the cutter, in fact.
Yeah.
Yes. Okay. Thanks.
There's another question there, Marina.
Just a short question, Barry. You didn't mention a local model or adaptive model. What do you think about? I mean, because this can be seen as a way of, model updating could be an alternative to model maintenance. Whatever you do with adaptive or dynamic latent variable model, or with local regression or whatever. So which is your feeling about this bunch of methods?
Yeah, I'll just take locally weighted regression as one that I've worked with the most out of that batch, and just say it seems that you have to have a critical mass of data in the areas that are new in order to make a local model work. So that seems reasonable, as long as you would then be able to make sure you are in the right space of that local model building. But yeah, I haven't tried that approach on it.
Okay, good. Thank you very much. We'll stop there. Thanks, Barry.